University of Warwick, and Christopher's going to talk about assimilation in climate research.
All right, thank you. Yeah, it's wonderful to be here. I'm actually visiting here for a little longer than just the workshop, and so that means you get an apartment. So I was put out in an apartment in West Cambridge, which seems to be colonized by Bill Gates, I think. And so last week I had to register my bike because there's big scary signs up everywhere saying you have to register your bike. So I go down to the custodian and he comes out and he says, "Oh, I'll register your bike." And he has this pen, this special pen. And he starts complaining to me about how he started off with 15 pens and 14 had been stolen. And then he looks for a minute and suddenly he looks up at me and he says, "Hey, you're one of Isaac Newton's lot, aren't you?" So I thought, yes, I am one of Isaac Newton's lot, although he made me feel like I was part of some gang. Anyway, so I'm pleased to be here and proud to be one of Isaac Newton's lot. I've been working on data assimilation. I'm really a dynamical systems person, but I've been working on data assimilation for the last so many years, and started thinking about how it might be relevant to climate. I started getting interested in climate, I guess, because I felt, in a sense, like Tim was saying, that mathematicians really have a lot to offer and somehow we're not getting on board and we need to start thinking about what we should be doing. So let's see, I'll go forward. So what is data assimilation, first of all? So data assimilation is the idea that you have observations and you have physical laws. The observations give you data, the physical laws give you a model, and you want to make optimal use of both of them to somehow give an estimate of the state of the system that you are observing. So you put this into the DA hopper and you get out some optimal state estimation or prediction. These are actually, I say both state estimate or prediction because those are two different sort of formats of data assimilation, and I'll try to explain how they both work in a minute. So this is the framework of the model in which you do data assimilation. A model is, from our point of view, a very, very large vector comprising all of the relevant dynamical variables, for instance, evaluated at the grid points of some computational grid. This is actually from a computation of the Gulf of Mexico. You can see a little bit of Cuba there. And this is the loop current and eddies spinning off the loop current. I have that because that's one thing that I worked on, is the Gulf of Mexico. So the model is something that advances the state of the system in time. The superscript F here connotes forecast, so I'll always use F for forecast for when the model is at work. The actual evolution is some unknown realization of a stochastic perturbation of that, so that includes the possibility of model error, and here I'm just assuming that it is delta correlated. Then observations are something that you make of the real system out in the world, which may or may not be observations of some of these variables here. You have the observation operator, which takes you from T here is truth, takes you from the truth to the thing you actually observe. O here is for observation. So in this picture here, the suggestion is that the observations are quite sparse. There are very few of them, right? And there are just 4 places where you perhaps are observing temperature or something like that. If these are actually at grid points, this could be a projection operator. If they're not at grid points, it may be some interpolation. Or if it's not a state variable, then this could be much more complicated and potentially nonlinear. Right? And then there's an observation error. Typically, from the point of view, our point of view, I think, and certainly, I mean, I come at this from working on ocean problems, and this is very, very true, that the dimension of the observation space is much, much less than the dimension of n. And then we assume that has some error covariance. So what is data assimilation? From what's called the sequential point of view, you start off with a truth here, so some true state of the system. That evolves up to some other time in some kind of messy way that the world provides for you. And you want to make estimates of this and of this. So your first estimate is your estimate of the initial conditions. This also has an F on it for forecast, even though it's a nowcast really. and you're going to prescribe some error covariance for that, which expresses your confidence in your guess of the initial condition, right? That is going to evolve under your model, sort of nice and cleanly as depicted here, and you're going to also want to give some kind of confidence estimate to your belief in the model. So you're going to want to have some PF, which would be possibly some error covariance, which represents your confidence there in your advancing from the initial condition. So that would include something from this, but also something about the model. You then perhaps make a measurement at this time t1, right? So to represent the fact that it's a partial measurement, this is just a two-variable system, right? So that in this cartoon. It's extremely simple. So what I'm going to suggest is that actually all we do is we can see one of the variables and not the other, right? And we do so with a little bit of error, okay? So how do we get now the optimal estimate of the system by putting those two bits of information together to get what we call the state estimate or the analysis here, and we want to give that also some kind of confidence, prescribe some sort of confidence to that. Well, the standard applied mathematician, I think, would look at this and say, well, do some kind of interpolation between these two pieces of information, right? So you would take your analysis to be your forecast plus some multiple of the difference between your measurement and what your forecast said your measurement would have been, right? This is called the gain matrix. This is not a square matrix, right? That's okay. So how do you actually calculate this gain matrix? All right, well, this is, sorry, I'll come to that in the slide after next, but assume that you have a way of calculating this gain matrix, and now think about how you put this together. So the idea is you're going to do this step by step. So you've got model and observations, and you want to make a prediction. You start at T0, you run the model to T1, you make an observation. You somehow do the interpolation in this way, you then update, you go back to T1 and you start again, you run the model again to time T2, you go through that process again and so on. All right? This is known as sequential data assimilation, and when it's called that, it's distinguished from variational data assimilation, which I find rather confusing because you actually can use variational methods in sequential mode. In some sense, it's a forward problem rather than an inverse problem, and it's also called filtering in statistics. That's the name that it goes by. Okay, so I haven't told you how you calculate the k. So how do we calculate this k? Taking the subscripts off, so making it sort of general again, you do this at each step. K is determined by the requirement that the analysis, xa, minimize a certain cost function. And that cost function is given here. It's the natural thing. It's just the least squares method, if you think about it, given your error covariances in the observation and your error covariance in your forecast, right? So that's just the natural thing, is to try to minimize that, but that allows you to actually calculate k, and it comes out to be this sort of expression here, which is well known from the sort of common filtering. That's exactly the expression for the gain matrix. But notice that in it that we've actually really had to assume everything is linear here. So H is a linearized observation operator if it's not linear to start with. R is the observation error covariance matrix, so that's something that you've sort of given yourself in the beginning. And then the question is, how do you determine this PF, right? So I've now given the K and reduced it to determining the PF. That depends on the data assimilation scheme that is being used. All right, so this is your formula here for updating. This is your formula for the gain matrix. And what are the possibilities for calculating PF? Well, first of all, you could assume that it was just constant. So you somehow know enough about your model that you kind of know what the error is in your model and it's constant. That usually goes under the name of optimal interpolation, or OI. If the model is linear, then you can just evolve PF under the linear model. That's exactly what the Kalman filter does. So that is the Kalman filter, evolving PF under the linear model. If it's nonlinear, then one thing you can do is you can linearize around a model trajectory and use the so-called tangent linear model, and you evolve it under that. That's called the extended common filter. Or you can do what's very popular now, is to sort of build it out of ensembles which are involved under the full nonlinear model. That's called the ensemble common filter. Okay, so that's very, that's kind of what are the, on this side of data assimilation, that's probably some variant of the ensemble common filter is the state of the art. So how does the ensemble common filter work? What you do is you take a bunch of initial ensembles here, approximating your truth, right? So you don't just take one guess and some kind of error. You actually take a spray of guesses, right? So you take ensembles. So it's a Monte Carlo ensemble of states, as said there. So these are subscripted now by J, and J goes up from 1 to NE, which is the number of elements in the ensemble. That evolves, that spray evolves up to here. And then what you do is you try to make an estimate out of that, okay? In fact, really all you do is estimate an error covariance out of that spray. What I've drawn here in the star is your sort of forecast, initial forecast and forecast at time t1, right? But that's just the mean of this. And actually you don't necessarily have to stick to the mean. The information you really want is your error covariance here. But if someone says, well, give us a model forecast, we want a specific forecast, then you just calculate the mean. To calculate the error covariance, you do the natural kind of thing. Okay, there's actually a little bit of an abusive notation with subscripts here. This J refers to the number of the ensemble rather than the number of the variables. So that's the ensemble common filter, how it works. But basically what you're doing with the ensemble common filter is you're exploiting the nonlinearity of the system, which is good because you're reflecting everything. The extended common filter, and so on, reduces it somehow to linearized dynamics or requires it to be linear dynamics. You're allowing nonlinear dynamics here, but to then actually make the update step, you're putting a Gaussian straitjacket on this. So you're effectively making it Gaussian by assuming that your error distribution here is encoded in this error covariance matrix. So it's kind of a sort of partly linear, partly nonlinear thing. It's kind of a compromise because this update step is the tricky step. Okay, you can also do data assimilation in state estimation mode. So this is a different way. It's a different set of problems that you would do this with. You would not be thinking about continually updating and stepping forward in time. What you do here is you take a model run and observations and get out of that some estimate of the state, but your model run and your observations would be given over a total time interval, let's say running from T1 up to Tn, right? So, and you assume that you're giving all of the information, the model runs and the observations from that whole set of time intervals. So what do? You start with an initial condition, x0. You would run the model, go time t1. You would then run it again, t2, and so on. You keep on going up to tn, and you get an x of tn. That's your model run, right? You've done that before you've done any data assimilation. You then make, right, and what you want to do, the goal is going to be to try to improve your estimate of x0. If you have a perfect model, right, you don't have model error, then that actually is the end of the story because you just go forward in time to get the estimate at each stage. If you'd have model error, then that's slightly different, but let's ignore that for the moment. So you then make observations of the real system, of the sort of truth out there in the world. You take eta of t0, eta of t1, and so on, and so there's an eta, is your observation of the state of the system x at each of these times here, and you assume you're given all of that, right? And then you want to put all of that together into the DA hopper to get a better estimate of the state of the system, or in our case, the initial condition of the system. And the idea is you minimize this cost function, and this is called 4D var, which looks like this, right? So again, it's rather sort of familiar, adding a piece which comes from the the sort of so-called background error covariance, which is to do with the model, and a piece to do with the observations. But you have all of the observations. So x0 star is your estimate of the initial condition, and b is your background error covariance, and everything is the same as everything else to start with. In principle, we do not have to assume that the observation operator here is h. It's natural to assume that the error covariance is, are error covariance matrices, and so it's sort of basically Gaussian distributions, but you do not have to assume that h is linear, but you do end up doing it in practice to try to solve this least squares problem. This is called variational DA. It's essentially an inverse problem, or it's called smoothing in the statistical literature, because it sort of in a sense also takes you back in time and smooths the whole trajectory back to the initial condition. So we've got these two different ways of doing data assimilation, right? So the key is data assimilation is aimed at this stage for getting an optimal state estimate, either in predictive mode by jumping forward in time and using data as it comes in to improve your sort of initial condition for going to the next stage, or it takes an entire set of information, model runs, observation, and so on, and out of that, through minimizing the cost function, gets you your best estimate of the state of the system. Let me give an example of this. This is actually, I think, a really lovely example of data assimilation, and so I always try to do this in talks, because I think it just shows you sort of the power of data assimilation. It's to do with a fish kill in Lake Kinneret. That is the Sea of Galilee. It was work of Guillaume Vernier in his thesis under Bob Miller at Oregon State in 2006. He then became a postdoc with me, and he's now working at NASA on their data assimilation scheme. But I learnt about this from Guillaume. And the thing is that occasionally, this happens in the summer in Lake Kinneret, there's a fish kill. So something happens to kill a whole school of fish, right? And they all die, and there's just sort of a massive sort of extinction of fish. So it's called the fish kill. And if you like, if you're interested in having kind of practical scientific explanations of stories from the Bible, then this is one, because this is a potential explanation of the feeding of the 5,000. Why they suddenly found on the shore of Lake Galilee, Jesus and his disciples suddenly found all this enormous number of fish, that they were actually just happened to luck on one of these fish kills. Anyway, Guillaume told me he wanted to actually reference the New Testament in the paper, and Bob Miller, who was his advisor, right, said no, he wasn't allowed to do that. Yeah, right, he put for author. The conjecture is that this is due to the lifting of a lower layer of oxygen-free water, right? So the idea is that there's a lower layer of anoxic water, and somehow it comes up to the surface, it catches the school of fish, and they all die because they don't have oxygen. So here's the analysis of that. So here's the model. There's a strong westerly sea breeze in the summer over Galilee, and it's stably stratified during the summer. So the idea is to take a two-layer model. The top layer represents the layer which has a lot of oxygen. The bottom layer represents the layer which is lacking in oxygen, the anoxic part, and you run it as a two-layer system. So here are the equations. You'll recognize the sort of shallow water type equations in two layers, right? So you got UVH for the top part, assume the density is constant, and then down here UVH for the bottom part with a different constant density. Okay, so here's the model run, and what you want to do is you want to look at the sort of separation between the top layer and the bottom layer, that sort of interface, and you want to see where that thing goes, and if that. Okay, so this is the run. So look at the way this is sort of flapping around, right? So this is the topography, the sea floor, this is the surface, and then this is flapping around. And the idea is it should go up to the surface and peek through it, and it doesn't, right? So you don't see this in the model. There's also some data here, so but not very much, but there is some data. There were two chains which are located here at F and at K, and they're thermistor chains. So they're chains anchored to the bottom and floating with something, kind of buoy floating them on the top, and then sort of thermometers up and down, so-called thermistors, which will measure the temperature. You want to think of, say, about 19 degrees centigrade as that thermocline is representing the interface between the top layer and the bottom layer, right? So the bottom layer, what you should see is cold water from the bottom coming up to the surface and peeking through it, right? So this is the data at these two stations here. So as you go through it here, you can see it sort of, you know, in a fairly oscillatory, semi-regular fashion coming up. And here, about the closest it gets to the surface is here. But it doesn't get to the surface. So you do not see this effect in the data either. But what if you assimilate the data into the model? Okay, so now we assimilate the data into the model, and it turns out you do see it. So it's a little harder to see, but you see this flapping around here, and as it goes over here, it actually kind of peeks up through here. Right? So let me show you on a comparison, and you can see it more clearly. So this compares. On the left is the model alone, and on the right is the one with data assimilation applied. And this is the sort of window in which this happens. And you can see here, look, it's sort of peeking up through the top layer quite clearly here, right? Whereas the model is not doing it. Right? So it's a fascinating application of data assimilation, right? You have a conjecture. You want to verify it. You have a model. The model does not verify it. You have data that doesn't verify it, but the data assimilation in the model does. Right? So it's rather a sort of extraordinary thing where somehow the data somehow teases out something that's there in the model. So anyway, I think this is a wonderful story. So this shows that data assimilation is applicable to religious studies. The question is it applicable to climate, right? So that's a much larger question and more relevant and poignant for us, I think. Well, in weather prediction, we know that data assimilation, yeah.
Just my curiosity, I mean, so the period when it did predict this coming up to the surface, was that an occasion where one of these fish kills was observed?
I think so, yeah. Well, I mean, okay, has that check been done? I'm not sure. I mean, since I didn't do the work, I'm actually not sure. Yeah, that's a good question. So in weather prediction, data assimilation is strikingly successful, right? I mean, it is used in weather prediction. It's thoroughly integrated into numerical weather prediction. Numerical weather prediction was really the original driver of the development of data assimilation as we sort of know it right now. But climate prediction, it seems in a way that neither approach, the sort of sequential or the variational, right, either the inverse or the forward problem, is quite sort of appropriate for climate. I mean, we're predicting, climate, you're interested in predictions well into the future. The philosophy is that if you take an atmospheric initial condition for today, it's kind of washed out in a few days. So if you're talking about decades or even more time ahead, then your initial condition is sort of irrelevant. So the sequential method isn't particularly good. You don't have data into the future, which is where you're interested in doing the predictions. So your state estimation method isn't all that useful, except for maybe improving the initial condition. We just argued that is not that important. So the conventional wisdom is that data assimilation is not relevant to climate. And I think when I've talked with climate scientists, that's kind of the point of view that comes across to me, that climate prediction is not an initial value problem, it's a forcing and a boundary value problem, right? I mean, it's replete with boundary value issues, the boundaries between the atmosphere and the ocean, I mean, the radiative forcing that's happening at the boundary of the atmosphere, and so on. And clearly, forcing is what's sort of forming the climate and the thing that we want to predict. So it's not a problem like that. So, but somehow I kind of wasn't satisfied with this, so I decided I would go and actually try to learn from climate scientists. And so I went to the CESM annual meeting at Breckenridge in June. So Judith can verify that I was there, right, since we saw each other there. So I figured, sorry? Yeah. So, I mean, the first thing that happened was I got there and they had changed the name. It was called the CCSM, the Community Climate System Model, and I thought maybe I was at the wrong conference because they were calling it the Community Earth System Model, but this was a name change that had happened just a few days before. But there's also, you know, and I am bearing my soul here, you know, if you're an applied mathematician, and one thing that I think that it's very important for us to do as mathematicians, as sort of Isaac Newton's lot, if you will, is to go out and talk to scientists in the other areas that we're interested in. But we know that the big difficulty of doing that, right, is lingo, right, is language, is acronyms and stuff like this, and you can make a complete fool of yourself. So I almost did. During the very first talk, Jim Harrell, who's the head of CESM, put this picture up. It was one of his slides that he put up in this beautiful talk he gave introducing the CESM, its strengths, its weaknesses, and so on. And I was about to stand up and say, he said, well, we've done various runs and we came out with these two different, he said we were interested in seasonal effects, we came out with these two different things. And I looked at that and I thought, my God, what are these people doing? They're getting two different answers and submitting one to the Journal of Fluid Mechanics and the other to the Journal of Atmospheric Sciences. And I was about to stand up and say, what kind of people are you? How can you do this? And luckily I stopped myself from doing that. And then I thought, oh, he said, yeah, seasonal, he said. Yeah, okay. A few minutes later, I want to, let's see, maybe I want to show this, which is, I think I'm on the internet here. So this is actually the web page for CESM, for the NCAR model. Mariana Wertenstein, I don't know how she pronounces it, was given the award for the CESM Distinguished Achievement Award. She's actually the head of the software engineering group. And I thought software engineering, that sounds really technical, that sounds sort of boring. And I was actually at the back of the room ready to walk out. And it turned out to be really, really interesting and obviously really important because they gave such a wonderful overview to it. But she also listed challenges for the new CESM. And number 3 was data assimilation. So I was heartened and I brightened up and sat back down and they are now incorporating data assimilation through DART, which is the effort led by Jeff Anderson on using ensemble Kalman filter, and that is now being incorporated into the ocean data assimilation at the CESM. But one thing, so what I learned from going to CESM, thinking in terms of, I mean, I was processing everything in my mind in terms of whether data assimilation was relevant or not. And I realized that it had two sort of beachheads, right? One was in paleoclimate. State estimation DA is becoming recognized as an appropriate and useful tool in paleoclimate. I mean, that was becoming clear. I know many of you here are using data assimilation in paleoclimate, so that's kind of old news, but the fact is that climate scientists at a major climate center are beginning to be aware of the usefulness of data assimilation in paleoclimate. And I'll discuss that in a little more detail in a second. The second thing is the ocean. So the IPCC AR5 has put a focus on decadal predictions, right? Rather than longer, say, centennial predictions, if you will. Rather than trying to predict what's going to happen in 2100, making better predictions about what's happening in 2020, 2030, 2040, and so on, with the idea being that it can be the basis of decision-making processes. Right? And the consensus is that if you do that, you need to get the ocean initial condition right. That is a key step in being able to make decadal predictions. And it's also recognized that data assimilation can be very useful in that endeavor, which is why DART is now being included in CESM for the ocean part. It's still not being used for the atmosphere, but it is being used for the ocean. There's a key issues in both of these areas which sort of join them together a bit. One is that you have very long time scales. The ocean tends to work on much longer time scales than the atmosphere. It responds on much longer time scales. The circulation of the ocean is something that involves currents which take, hundreds of years to sort of complete. And they also have sparse data. Right? Well, data is obviously an issue in paleoclimate, especially as you go further back, right? But in the ocean, in the deep ocean, it's also particularly an issue. So actually, we had run right just before the Breckenridge meeting. Jeff Anderson and I ran a meeting at NCAR through IMAGE on data assimilation and climate research. It was just the week before. I actually want to make a plug for IMAGE. IMAGE is an institute at NCAR, the National Center for Atmospheric Research in Boulder, which is headed up by Doug Nitschke. It's the Institute for Mathematics and Geosciences, and the idea is to try to bring mathematics into NCAR and to engage mathematicians with climate scientists at NCAR. And I think it's a good model, and I think it's been quite successful. It's certainly been useful for me. There was one talk at our meeting by Gerard van der Schreer, and he talked about this work he did with Bachmeier. So this is on the paleoclimate. And I want to go through this rather sort of carefully to give kind of an idea of how it can be used in paleoclimate. And it's slightly reminiscent, I think, of the way that it was used in the fish kill in Lake Kinneret, in that it's a question of setting up a certain hypothesis and using data assimilation to either confirm or deny that hypothesis. This is actually, I think, rather similar to work that Jonty and Michel have done, Crucifix and Rougier have done in the same kind of style of using data assimilation. All right, so this is about the Dalton minimum period, which ran from 1790 to 1820 approximately. It was a period characterized by cold in Western Europe. It was known that there was decreased solar activity during that time, and there were also a couple of volcanoes. The origin of this one in 1809, I think, is unknown, and the one in 1815 is actually known. These were during this period, but obviously the volcanic dust activity from these can't explain why the cold would go back to 1790, right? And in fact, work on comparing the effect of these two things suggested that it was volcanic dust uploading that was more significant than the decreased solar activity. But they took a different approach, and they looked at what Bjerknes hypothesized. So Bjerknes hypothesized, said, forget for the moment what maybe the primary cause of this is, forget the decreased solar activity and so on, and think about what is maybe connected in terms of different kind of climatic events. And he hypothesized that there was an anomalous ocean-atmosphere interaction which was somehow responsible for a southerly flow of cold polar waters into the northeast Atlantic Ocean, and that then caused Western Europe to get colder, even into the summer months. So, and I think the idea here is that whatever the overall primary effect is, it can't explain regional differences anyway, and that Western Europe was colder than it should have been, even given these other effects. So the question was whether this anomalous ocean-atmosphere interaction could explain what was going on in Western Europe. So, and there's data from this. There's some data on sea level pressure, which, and this is the average pressure anomaly over that entire period of time from the Dalton minimum. And there's a sort of uncharacteristic high sitting over Iceland and a low sitting over Labrador, right? And that kind of anomalous situation, you can argue from Sverdrup's principle that that should cause a flow of cold water down in this direction here into the northeast Atlantic. Okay? This is the data, this is a reconstruction due to Lutherbacher and others, which shows the sort of, I think, the winter climate and the cold temperatures. So the question is this related to this? So physically, Bjerknes had given an argument for this. The question, though, was whether you can quantitatively tie these two things together. So they introduced a data assimilation technique to assess the relationship between these two things, the anomalous SLP and this cold period in Western Europe. They based it around EC-built Clio. This is actually a slide I borrowed from von der Schreer. He gave during his talk. He's at KNMI, right, which is the Dutch Met Office. Oh, sorry. And so EC-built Clio is an intermediate complexity model. It has sea and ice. It has approximately 3 degrees resolution, 3 degrees by 3 degrees resolution. In the atmosphere, it's QG with forcing taking up, parametrizing the non-QG effects and so on. And what they did is they used this and then they assimilated into it the data that came from the SLP, the sea level pressure anomaly. So this is a QG stream function, and this is sort of the target, which is approximately what I showed you in that color picture before, that is to be used in the data assimilation. And this is the result of the data assimilation. And I couldn't find a journal associated with these initials, so I figured it had to stand for December, January, February. It seemed like in Europe, the winter's December, January, February, but in the States it's January, February, March. I don't know. Anyway, so this is the difference between the DA and the control runs. Okay, so this is, you've done the data assimilation. You actually have assimilated. I'm not going to talk about their data assimilation technique because that would be a whole hour, right, to get into that. It's just they have a black box, which is a data assimilation technique. They're invoking it to assimilate this kind of data, and that's going to nudge the model runs. And the control run is no data assimilation. This is with data assimilation, and this is the difference between the stream function plotted by its contours here. And you see that you reproduce this high, although it's shifted a bit, and you reproduce this low, okay, as seen in those differences. Okay, so that's sort of encouraging that when you do the data assimilation, you do reproduce the hypothetical situation of the ocean atmosphere anomaly. This is then their result, okay, and I'll just let their own words say it. This is taken directly from their paper. This is the difference in the 2-meter temperature averaged over the 25-year period. Actually, there wasn't, so it was a slightly shorter period than the full Dalton anomaly for the winter and then for the summer, okay. So you see that this is, and then this is the comparison of the Lutherbacher reconstruction. So you see, I mean, this is the grid size here. There's reflecting the EC-built Clio grid size. That's why these grid boxes are rather large. But you can see that it predicts a colder Western Europe and a warmer pieces in North America in both the winter and the summer. And you can see that that is exactly roughly what happens in the actual reconstructed temperature record. What they're getting, what's causing this is exactly what was hypothesized by Bjerknes, is this anomalous wind stress curl. This is a patch of negative wind stress curl here, right? And this is the SST difference between the DA and the control run in the winter that you get from this. So this is the sea surface temperature, the change in it being caused by this sort of what must be this flow of southerly polar waters that's manifesting itself in the model through having assimilated the data which sets up the ocean-atmosphere interaction anomaly. All right, so their conclusions are the following. This anomalous ocean-atmosphere interaction is directly related to the Western European cooling, so you can see that. If you don't assimilate it, this data into the model, and you don't see the cooling. If you do see the cooling. It's independent of the possible primary forcing. They did not change the radiative forcing in this at all. So they did not change the solar activity. They didn't introduce any effects of volcanic dust uploading. That may indeed have been there, and you could imagine another experiment which put that in to see if that actually set up, put that in, say, by data assimilation, to see if that set up the ocean-atmosphere interaction anomaly. That would be conceivable too. The really interesting thing, though, is that they saw an MOC weakening, right, a meridional overturning circulation, right? I mean, I think, at least from those of us in the non-climate lay community, if you see cooling in Western Europe, the usual suspect is cutting off of the Gulf Stream or reducing the Gulf Stream, right? So they saw that weakening, but it was not statistically significant, right? So that was not a part of the cause of the scenario here. All right, let's go back to data assimilation. There's something really unsatisfactory about this picture, right? This picture is the applied mathematician's picture, and it says, we want a particular answer here. We want to get the best estimate out of taking the model with some confidence and your observation with some confidence. But we want to get out of it a single number. But really, a statistician would come along and look at this, and does come along and look at this, and say, but you're throwing away lots and lots of information. You're throwing away all the interesting information. And what you should really do here is Bayes' theorem. Right? You should really apply Bayes in this instance. And actually, what the primary thing here is not your specific guess here, but is your error confidence expressed as a whole PDF. So the optimal solution is not really the specific answer you get, but it's the probability distribution function, right? And okay, if you want to take the mode of that and so on, then you can do that if you have to have a specific answer. But really, your full set of information is encoded in the PDF. And Bayes' theorem tells you how to do that. It tells you that the posterior probability, that corresponds to the analysis here, of the state of the system given the observations, is the likelihood of the observations given a certain state of the system times your prior ascribed probability of the state of the system. Right? So this is your PF here. This is your epsilon, your P obs. This is your likelihood. This is your posterior, your analysis. And this is what you should really be doing. Now, if we push that even further, and you start thinking about it, and you think about this whole picture here, you realize that there is one piece of this picture which is completely redundant, which actually appears in nothing that you do, and that's the truth. Right? That is actually, right, you start feeling sort of dizzy at this point, don't you, right? You start feeling like you're on shifting sands, right? You can't throw away the truth, right? But actually, in terms of the analysis of this thing, even in the sort of, deterministic idea of setting a particular variable, it's the truth just does not appear, right? But it can't, because you don't know it. I mean, what you're doing here is you've got information from the model, you've got information from observations, and you're trying to put them together in the best way you possibly can. You got this information, and this is your cumulative probability distribution function for the state of the system. That's the information that you have. Okay, well, so the key, though, here is going to be, in some sense, you can think of it as calculating this prior here. I mean, this is something, presumably you've decided how good your observations are, so it's your prior here that you want to get, right? So how do you do that? Well, you evolve under Fokker-Planck equation. So here's back to our x1, x2 cartoon. So you have a PDF here, and you evolve the PDF here. This is the model here, this is the model error, it's the Fokker-Planck equation, and this looks like a very easy thing to do. You then have an observation of one variable and you put those together and you get a new PDF, and you use the Bayes step to do that, and so on. And this looks all hunky-dory, you're finished, right? The only problem is that the number of independent variables here is 2, but this is a simple cartoon. And if you had the state of the system being something like the atmosphere or climate, 10 to the 6, then you would have 10 to the 6 independent variables here. You have trouble solving this PDE when you go to maybe 3, 4, 5, something like that. But 10 to the 6 is completely hopeless. All right, so that's why we're still in business, right? I mean, so to say Bayes' theorem is solving data assimilation is a bit like saying, well, fluid mechanics was over when the Navier-Stokes equations were written down. So, all right, let me make a connection between the posterior and the cost function, because this is rather nice. So on the predictive level, the posterior distribution actually can be written as the exponential of minus the cost function, right? So there's an intimate relationship between the cost function and the PDFs. In state estimation, it can be written like this. It's the same thing. And the minimization will always give you the posterior mode. So if you're doing 3D var, 4D var, or whatever, you're actually getting one particular piece of statistic from your PDF. Lest you think that that's a sensible thing to do, just finding the posterior mode, it's always refreshing to look at the Lorentz equations, right? This is actually a log posterior, in other words, the cost function of Lorentz 63. This was done by Jochen Voss, and you see this if you try to find the mode of that, you really would walk away and question whether you'd gotten sensible information for yourself, right? You want to have the whole thing. And we wrote this up in a paper, this idea of the posterior and the cost function, although I think it's older. All right, I want to do one example here to explain why we should really do the sort of statistical approach and not the deterministic approach, and that's because of nonlinearity. So you're always assuming in this sort of deterministic approach that things are Gaussian, and there's always a linearity assumption hiding in there, right? And those go together because linear systems evolve Gaussians to Gaussians, right? Which all looks very good. But the problem is that nonlinearity really does mess you up. And here's a very simple example of that. So this was motivated by work in the ocean and looking at Lagrangian data, and we're just looking at a simple model here to understand the phenomenon. This is the linearized shallow water equations. This is a particular flow field, a particular cellular flow field, all right? And we looked at different trajectories in here, and we wanted to sort of estimate these parameters, U1, and then the time-dependent parameters of the first mode. These are sort of, Fourier mode solutions of the linearized shallow water equations. All right, and so these parameters satisfy these equations. So what we do is look at a trajectory of this system here. X dot is U, Y dot is V, and from that trajectory try to reconstruct these things. So it's like you've got an Eulerian flow and you're looking at a fluid particle going around and you're allowed to know the position of it. What can you say about the Eulerian flow? And we compared an ensemble Kalman filter and a Metropolis Hastings, which is a sampling strategy for getting a handle on the PDF. Okay, so this is a statistical approach here, and we took one trajectory inside the cell. This is the truth here, is this vertical line. We took 3 different observation sets, and these 3 different observation sets, I'll explain observation set 4 in a minute. The 3 different observation sets are with decreasing frequency of observations, right? So you expect to do worse and worse, right? So, and here's the PDFs. They're pretty much on top of each other, the one for the ENKF and the Metropolis Hastings, right? I mean, this has to be Gaussian. This happens to be almost Gaussian. So they sit almost on top of each other here. But here they separate. When you go infrequent enough observations, the ENKF does a lot worse than the Metropolis Hastings. So then we asked the question, well, can you go further? So keep the same frequency of observations, but go further along the trajectory and keep observing more, and then see if you can improve your estimates here. And the answer is that you can improve the metropolis Hastings, but you can't improve the ensemble common filter. So something's already gone wrong to mess you up. And we figured out sort of what it was, and it's just a very simple nonlinear effect. So here's our first observation. After the first observation, here's our spray of ensembles, right? So it's like a Gaussian. Looks very nice, right? Before the second observation, however, what has happened is that, you know, your little spray of ensembles here has suffered under the effect of nonlinearity, which has an amplitude-dependent period, right? This is like an oscillation around here, but as you go out, the period gets longer, and in fact, the ensembles have spread out into a donut, right? And the ensemble common filter is trying to make a Gaussian out of that. What you get afterwards, after the second observation, is indeed that sort of Gaussian. This is using the ensemble common filter, right? But you've lost all of this nonlinear information. And for some reason, there's no way you can recover from that. Okay, let me just finish up. I'm sorry. Oh, I'm going over, aren't I? So I'll just take a couple of minutes to finish up and talk about climate models. This is just to sort of finish up, right? I really... as I say, you know, I was going out to Breckenridge to try to learn what climate scientists do, so I don't have anything deep and unequivocal to say about climate models, but I have some thoughts that I hope may be interesting and provocative. So this is a climate model. These are the primitive equations of GFD solved on a grid. That's essentially the dynamical core of the model, right? And in a sense, a lot of climate science goes into forming these Fs, right? This is sort of what Tim was talking about, all the parameterizations that go into making up these forcings here, right? So this is, Doug Nitschke calls this the craft of the climate scientist, is to form these forcing terms here. That includes parameterizing subgrid processes, parameterizing missing effects, information flow to other parts of the model, setting ambient conditions, radiative forcing. Obviously, you know, if you're doing it under 20th century conditions or so on, that comes into these Fs, right? But it also includes tuning the model, right? And that's sort of what I want to talk about a little bit here, is tuning the model, because it seems to me that this is actually a place where data assimilation potentially could play an important role. What happens in tuning the model? Oh, I got my PowerPoint wrong here. You start with model runs, and this is what I sort of gleaned from talking with people and just in the last few months. And out of that, you get your model output, which you check. You then go back and reset model parameters. Now, what you're doing here is you're going to look at various key signatures about your model. Does it do the things you expect it to do? So does it give the correct ice thickness? Betty Otto Bleisner, who's a climate scientist at NCAR, said to me, well, we're getting more and more data now about ice thickness. So we can go back and we can reset, retune the models to try to correspond with that better data. From the ocean, do currents lie in the correct locations? Is the tropical precip right? I mean, everyone would have their favorite key signature that they would want the model to adhere to, so that they can believe the model. Right? So this is somehow based on accumulated experience, and then the resetting of model parameters comes from the sort of expert judgment based on that accumulated experience. But it seems to me that underlying this accumulated experience somehow is observations, which can translate into data. I mean, somewhere underlying it are observations, because you know, you see the ice thickness now, so therefore you can try to make it correspond to the ice thickness. It seems to me that behind this there are some preconceptions that I would question. The first is about uncertainty, and that is that we sort of see uncertainty as become to be seen operationally as an intrinsic property of the model or a collection of models. And if you look at them hard enough, do multi-model ensembles, single model ensembles, we can somehow estimate the intrinsic uncertainty. But it seems to me that the uncertainty has its origin in many, many places. For instance, in doing this tuning of the model, the expert judgment and so on. And perhaps we need to unpack the model to try to see how that uncertainty is put together, right? Unpack the operational formation of the model. I think part of the problem here is the way the IPCC works, because every 7 years the models are declared stopped, right? As the IPCC says, you have to have papers in by a certain date. Each climate center then works backwards from that date and says, okay, the model as of April 1st, 2009 is the model that's going to be used in AR5. And maybe there's clandestine tuning of parameters after that, I don't know, but it's pretty much done at that point. And all the tuning and everything has now become part of this massive package, which you can only deal with in Unity in its own right? But I suggest that maybe we need to unpack the model to understand the uncertainty. The other thing, which I think I'm a much more solid ground on, this is, I have a little bit of a nerve stepping into climate science and saying stuff like this, but in data assimilation, I feel comfortable, and that is that everyone is wrong in thinking of data assimilation's primary use as getting the best estimate. And I think that's still the way climate scientists think of data assimilation, that a way it's going to help them. When in fact it tells us how to put information together from models and data and tells us how the cumulative error is formed. And that could be arbitrarily complex. And the issue is, how do you sample the PDF, right? That is the issue. That's a big issue, but that is the issue. Okay, so I claim DA. The point is that DA, I think, could be used in tuning climate models effectively. In a way, its use would be similar to the way that the paleoclimate work of von der Schreer and Bachmeier, right? Because it would be, you're plugging in some data, right, which corresponds to the phenomenon that you think your model should be capturing, and you are then running the model and assimilating that data and seeing what comes out. So you're actually getting for yourself some, and at the same time, you're going to get some kind of idea of the uncertainty that's come from these two different pieces of the operation, running the model and doing the tuning based on these observations. Okay? So again, it's absolutely critical to take the Bayesian perspective on this. So what are the challenges? Well, the issue, though, of doing this, of course, is that data assimilation is nowhere near ready to be applicable to the climate. Right? If you view it certainly in this sort of Bayesian perspective. So the issues to be dealt with is we have to deal with high dimensions, we have to deal with nonlinearity. So the key in that, I did that very simple perturbed cellular flow field example. If that had been actually a full solution of the shallow water equations, we would have been lost, because doing Metropolis Hastings at that level is pretty hopeless. Particle filters are an extremely successful way of sampling the PDF in low dimensions, but we know that doesn't work as you go to high dimensions. There's a paper by Bengtson, Schneider, and Bickel, which shows that the number of particles you need increases approximately exponentially with the dimension. So it gets hopeless very quickly. So we need to figure out ways to deal with these within the framework of the sort of Bayesian perspective. Multiple time scales, obviously. Like if you're doing paleoclimate, do you assimilate average data, or do you try to assimilate the data and then average? But we really need to shift the perspective from getting the best estimate to finding the PDF that represents all of the information. That seems to me to be really, really fundamental. And that's it. Sorry, I went over. Took a while.
Time for a few questions. Yes. Just say who you are and where you're
Can
from.
I ask a beginner's question about...
You've got to say who you are.
Well, where you're from.
I'm a statistician, so I know nothing
And you're from Durham.
about data assimilation or climate science. But, so, the thing that I was trying to understand in your talk was that the models that you run have a collection of parameters whose values you don't know. Okay? So,
Well, I don't run the models, but
well,
yeah,
I mean,
okay.
if you want a climate model, I mean,
Right.
like, climate models are full of, like, what is plankton doing, what does this do, what does that do, okay? So I can see two ways of data assimilation. Is that I could either run for fixed choices of the parameters and assimilate the data per model, or I could, in some sense, try to incorporate my parameter uncertainty by generating the ensemble for my ensemble Kalman filter. Now, I'm trying to understand how these things would work, because my natural way of thinking about it would be that I see the data, and I use the data to constrain the model parameters. Having constrained the model parameters, I repropagate the state vector. And that seems quite different from what you're doing.
No, I don't think so.
Or, it, well, it, yeah, I'm
Well,
trying
first of all, I mean, that setting the parameters at the end here is something I haven't done. This is just sort of speculation, but and it sounds to me like that would be a sensible way to do
So do you treat
it.
the model as a model which has no unknown parameters?
Well, I think that's sort of what the IPCC forces on you, right? On April 1st, 2010, or whenever the date your climate center decided your model was done, then I think that had its parameters set. Tim, is that more or less correct? I mean, its parameters were set, so you...
I think you said it correctly, that in meteorology, data assimilation is primarily used for initial value estimation. So it's
Well,
a way
initial
of
value-
determining in the initial...
But is that for a tuned model for
Yes.
the parameters of
Yes.
the set? Yeah.
Yeah, it's for
Yeah.
determining the winds
Fine, yeah.
and the pressures.
Yeah.
And
Okay. So it seems to me then, if one's really talking about the Bayesian challenge, of course, you may have set the parameters for a particular model, but the reality is that these parameters are unknown.
Yeah, that's what
And
I'm
the
saying.
data
Yeah. That's
constrain
exactly what
the
I'm
model
saying.
parameters as well.
That's exactly what I'm saying.
And so it seems to me, in some sense, it's easier to estimate the model parameters than the state vector, because the model parameters are like a
Right.
50, 100,
Right.
or...
Well, using data assimilation to tune the model, that's what you would be doing.
Would you use data assimilation per choice of model parameters? So I choose one set of model parameters, I use data assimilation, I choose another set of parameters, I use data... So we should probably continue this.
Yeah, we should
not
do. No,
quite.
I think I'm saying the same
I think
thing.
you mean treat the parameters like observations.
Yeah,
Yeah.
I mean, this talk sounds quite similar to, I'm James Annan, I'm in Japan at the moment. It sounds quite similar to the sort of work we have been doing, where we're augmenting the standard approach to doing the parameter estimation problem in the same framework is to augment the model state with the parameters, so then they become like variables that just have a stochastic evolution, or no evolution even, but they just have an initial prior. So in some sense you can do the whole problem, but there are obviously very large practical difficulties in actually getting good answers. But there is some theory that under which it should work.
Take three more, and then we really do need to break for lunch. Can you have Dan first, please? Could you just introduce yourself?
Dan Cornford, I'm from Aston University. I work in data assimilation. So you made a comment that truth doesn't enter in anywhere into that framework, but I quite strongly disagree with that, because your observations are observations of reality, and your model, the only link between your model and your observations is through some common idea of what reality is. Otherwise, you find it very difficult to formulate a likelihood in any sensible way. So how do you, would you stick with that statement that truth
Yeah, I
or
think so.
reality is...
I mean, why? I'm not sure that I see why you need it to. I mean, this could be a philosophical discussion. I mean, truth is an unknown realization of the process, right? But you don't. All you really know about that is your observations, which is some. I mean, if you're doing an identical twin experiment, then you do some realization of your process, right? And your observation is of that with some error, but you don't know it.
You're not doing an identical twin experiment. There's reality and there's
Yeah.
your model. And
Right.
the only link between those are really through your observations. If you don't specify your Q and R matrices or your PDFs, if you extend that, how can you frame the
But
problem?
that's sort of your, yeah. Well, I think that is kind of a philosophical point.
It's a very familiar philosophical discussion from 70 years ago in other branches of physics, but you're saying you're building a theory of classical measurement, right? So the objects that enter into your theory are measurements.
Right,
Full
right,
stop. It doesn't preclude the existence of reality.
right.
It says that you can
Right.
it says that you can say only what your theory of measurement. You're saying that physics is a science of measurement,
Right.
and that's the objects in the theory. Yeah?
Right, right,
Basically.
right,
Yeah.
right. And my confidence in that measurement.
John D. Rouge at University of Bristol. I now have 3 questions to respond to. Nick, yes, basically your this is an instrumental view of models, isn't it? Where models, the purpose of models is not to represent or not represent reality. That question is left unanswered. But the issue is whether they're useful for making predictions about the system. With respect to Michael's and James's questions, augmenting the state vector with uncertain static parameters is known to fail for all but the most trivial of problems. If it works for your problem, then your problem is trivial, and there's a better solution than doing data assimilation. That would be the first point from the statistical literature. But with respect to Michael's question, the purpose of data assimilation may be thought of as a quick way to compute the likelihood, the marginal likelihood of a particular choice of model parameters. So in that case, you would do data assimilation on a per parameter basis, yeah? And each data assimilation run would therefore give you a score, yeah? And then those scores could be combined into a weighting or a reweighting of the parameter space, which is effectively statistical calibration.
Okay.
Two more points, then we really do have to break for lunch. We're going to be running late at the end of the day. One from Julia at the back and then Tim to finish.
I was going to say the main problem with the data assimilation, that you were saying it should be useful for modelers, right, for tuning. The main problem is the having to do it about 100 times, and the models are built to run about once.
Right.
I mean,
So
you're saying your
the main problem is sampling the PDF.
So you've done quite a bit of the data assimilation for the climate models, looking at the equilibrium state, and we're always doing it with a cut-down version. So it's not directly useful to the modelers at the time they're building the model.
Yeah.
They're always asking us, can you help us? And we say,
Good to finish off. Tim.
I just want to make a comment, so all you have to say is yes at the end of this. Which is that your question is data assimilation relevant to climate research or climate prediction? And I definitely think the answer is yes. But I have a reason which is, I think, a little bit different from what you have described so far.
Okay.
And I spoke in my talk about biases, and that's been a really long-standing endemic problem of climate modelling. And one of the issues that you get to when you're addressing bias, which I think is implicit in what you said, but it's this problem of kind of compensation of errors. So this problem, for example, of sea ice being not thick enough, let's say, you could fiddle around with the sea ice parameterization, but it may be the case that the real source of your error is the fact you don't produce enough of those types of blocking things that Barkmeyer was looking at. For other reasons, could be the topography in the model is wrong. Something is wrong, which produces insufficient of that type of flow, which therefore leads to insufficiently thick sea ice in the North Atlantic. I mean, that could be.
Right.
So you get this problem with two completely different potential solutions to your problem, giving the same kind of effect.
Right.
Now, this is, I think, one of the really important applications of data assimilation to climate modelling, is that if you have a set of initial conditions where you've assimilated data, and you run your climate model over for climatic timescales, very short timescales. It could be a day or even a few hours, or even one time step actually of the model from those data assimilation data sets. You can see which processes the model is drifting away from before all these kind of nonlinear interactions have started to build up and interact with each other. So if there's something wrong with the topography, you'll see that by focusing on topographic effects. Or if it's something wrong with or maybe sea ice is a tricky one because that's a rather long time scale process. But you can isolate processes that actually are leading asymptotically to your biases in ways that you can't do by just looking at the model once it's gone on to its attractor or whatever it is.
Okay.
So data assimilation, I think, plays a really important role in being able to isolate processes that you're getting wrong in your model in ways in which conventional diagnostics can't do. So that's another reason why I think the answer to your question is definitely yes.
Yes.
I have some specific. I have a specific example of how this has worked.
I'd love to see
I won't
that.
talk about it now.
Yeah, I'd love to see that. Yeah.
Okay, well, thank you very much, Chris.
All right.
And,
Thank you.